Hi everyone. I just received this question some time back, so I thought I'll discuss it. It's not a analysis question; it's more of a design question. So I thought I'll very briefly tell you qualitatively how to go about solving this problem. So it's a circuit. It's actually a multi-stage amplifier. I will come to that. What are the stages and all that? So you have. It looks like a complex circuit, but it's actually a very simple. But it's actually a very simple circuit if you actually split it into smaller parts. And the circuit, the core of the circuit, the input is applied to the source of transistor M1 and the output is at the source of transistor M5. And you are supposed to design this with a gain greater than 50, and the power dissipation has to be less than 25 milliwatts, meaning the current drawn from the supply, the average current drawn from the supply, if I multiply to the voltage, so VDD is given to be 2 volts. So the average DC current that you're drawing from the supply should be less than 12.5 milliamperes. Gain should be greater than 50, and the output swing. So the output is assumed to be undergoing a swing, and the peak to peak, the total swing or the total peak to peak variation at the output should be greater than 0.8 volts. We'll assume it's equal, we'll design it for equal to 0.8 volts. Okay. And the load resistance, it's a resistive load at the output, it's given to be 100 ohms. That's it. There are no constraints on bandwidth, so there is no constraint on frequency response. So here it's more like a DC analysis. So probably the goal of I'm assuming the person who designed the question had DC analysis in mind. So before we go there, whenever you have a complex circuit, see if you can break it down into smaller parts. Okay, just see if it has some simplicity or simple repeating patterns in them, then you can analyze it much easier. The first circuit, if you look at the first transistor M1, input is at the source, output here is at the drain. So it's a common gate amplifier. So this part, the upper transistor M2 is just a biasing transistor. It's a common gate amplifier. The second stage is a common source amplifier. Input is at the gate, output here is at the drain. Okay, that's what is feeding into the next stage. The third stage is a common drain amplifier. So it's a common gate, common source, and common drain cascade. Okay, so that much we understand now. Now I'll just quickly refresh your memory. So these are all different configurations. So first, if you look at common gate and common source transistors, they both are driving current source loads. Okay, so another thing I'll probably make it clear now itself is the common gate and the common source amplifiers are driving capacitive loads. So if you see the load here is a capacitor. This is also looking into the gate, so it's a capacitive load. And the final stage, which is a common drain amplifier, it is driving a resistive load. Okay, so before we start splitting the gain and all that, so first let's quickly analyze the common gate and common drain amplifier. So common source amplifiers. So a common source amplifier with a current source load. So here current source is a PMOS device. So let's call it M3, M4. And so if you're given this device, the voltage gain of this device is this configuration. If you're given this configuration, it will be minus of GM3 into RO3 parallel RO4. Let's assume for simplicity, the output resistances are same for PMOS and NMOS. You have designed it in such a way, then this will be approximately equal to, in fact exactly equal to GM3 into RO3 by 2. In the same way, for a common gate configuration, where I'm assuming the load is again a current source load. Okay, so let's this device be M1 and M2. I'm applying input at the source. I have already derived this previously in one of my lectures. You can go through the low frequency analysis of a common gate amplifier. How can you analyze it? You can draw the Thevenin equivalent of M1 which is a common gate circuit, Thevenin equivalent, the DC or the open circuit gain for a simple common gate amplifier, M1, if I apply input here and take output here, it will be 1 plus GM1 RO1 times PI. And the output impedance looking at the drain terminal with the source grounded and gate is also grounded is RO1. So I've reduced a common gate amplifier to a simple voltage divider with a gain. So you can quickly show the voltage gain will be 1 plus GMR0, that's your open circuit gain, times RO2 by RO1 plus R2. This is due to loading, the current source load that we have connected. Again, if I assume RO1 to be close to RO2, the gain can be approximated to GM1 RO1 by 2. Now, if you look at common source and common gate configurations, the DC gain is more or less the same. And if I bias, for example, the transconductance of MOS device is proportional to root of mu n Cox W by L into the bias current I, and the output impedance is proportional to the output resistance or the drain resistance 1 by lambda into the drain current. Let's call it ID as the drain current. Now, if I take the product GM into R0, we call the term as intrinsic gain. Your GM into R0 is proportional to root of W by L by the drain current, root of drain current. So which means if I bias common source or common gate amplifiers with lower and lower drain currents, then I will get higher and higher gains. So I want to get a high gain, I have to bias it with lower drain currents, or I can keep the bias current same and the device length same, and if I just increase the W by L ratio, then also my intrinsic gain increases because your GM is increasing. R0 is fixed, but GM is increasing. So you have to keep in mind when we analyze MOSFETs in an introductory course, first level course, we introduce what we call the square law characteristics. The square law characteristics are derived assuming, where your drain current is proportional to VGS minus VDH the whole square. You have to keep in mind these results are valid for strong inversion. So a strong inversion generally means your VGS is much greater than VTH. It's usually at least 150 to 200 millivolts and above. Okay, your VGS minus VTH should be usually, it will be greater than 150 to 200 millivolts. Okay, so then we say the device is in strong inversion and the square law characteristics hold true, and these equations work fine. Okay, but when you actually start designing circuits, so you have to keep in mind that the actual MOS model is a lot more complicated than a square law device. Okay, you would have a dependence on different node voltages of the MOS device and more parameters than what we normally introduce. We just care about W by L ratios and oxide capacitance. It will have some additional parameters as well. Okay, so that makes the mathematical modeling complicated, so we have to rely on simulation softwares. Then why do we teach you all the square law characteristics? The reason is that this square law characteristics helps you in forming certain intuitive understanding of the MOS circuits. We get a feel for what is happening in the MOS circuit. So when you're going to design it, otherwise it will just look like if you're just going to sweep your dimensions and find the right gain, right dimensions and currents and everything, it will not look intuitive. It will just look like a black box and you won't know what's happening inside. These results, they are not exact, they are approximated, but they give you a very good understanding of what's happening in the system. Okay, when you are sweeping different parameters and you know what's exactly happening there, which is why we use the square law models as an introductory part, as an introductory part of any MOS device course. Now, there are a few points which I'll explain now. Probably when I float this course on CMOS OPAMP design, I'll go much deeper into it. But right now, the expression for MOS transconductance is mu1 Cox W by L times the drain current is proportional to this. So this result tells you for a given drain current, if I want to keep increasing my, if I want to increase my transconductance, all I need to do is just increase my W by L. So this result shows that if I just, it's of this form, GM square is proportional to W by L. So if I plot GM versus W by L, this tells me that, okay, it's like a parabolic curve, y square equal to x kind of curve. It just increases like this. Okay, for both are positive, so it will increase, it will be in the first quadrant, it will increase like this, monotonically increase. In reality, however, you will see that after a certain value of W by L, your GM saturates. For a given drain current, there is a fundamental limit of GM which you cannot exceed after a value of W by L. This happens because at some point, as I said, these equations where GM is proportional to root of W by L is valid if the device is in strong inversion, when your VGS is much greater than VTH. As you increase your W by L ratio, for the given drain current, the MOSFET's VGS will start approaching VTH. At some point, when your VGS minus VTH is less than 100 millivolts, so usually the number is 4 VT. Remember, VT is your thermal voltage, which we introduced for BJTs. When it is less than 4 VT, which is approximately 100 millivolts, assume VT is 25 millivolts at 300 Kelvin, so approximately 100 millivolts, the device enters subthreshold, and the characteristics, the drain current, then becomes exponentially dependent on VGS. Okay, so it has an exponential dependence on VGS minus some eta VT, where VT here is thermal voltage. So now we know that for a BJT, the transconductance is proportional to the drain current. It is actually drain current, or for a BJT, it is collector current divided by VT. VT is a thermal voltage. For a MOSFET, it is going to look like something like ID upon 2 VT. Okay, where VT is a thermal voltage. I can rewrite this expression as 2 ID upon 4 VT. So in the form 2 ID upon V overdrive. So this is your GM. So that's why I said when your V overdrive is greater than 4 VT or less than 4 VT, which is 100 millivolts, the device generally enters subthreshold or weak inversion region. In weak inversion region, this is the characteristic the device follows. The mathematics for it, why it does, you'll find it in any references, I think you can just search for it on the internet, or any good books on MOS modeling should have this. But for circuit designers, of course, the physics part of it is not important. The final result that we have is that it's exponential, which means the transconductance GM no longer depends upon W by L, and it becomes linearly dependent on the drain current. So if I increase my drain current, I can expect my GM also to increase like this. Okay, as you increase your drain current, your GM will increase. The maximum attainable GM will keep increasing. So using this, I can argue that the intrinsic gain that you can get GM times R naught, because your drain current is proportional to I, R naught is inversely proportional to I, the product will be like a constant. So even you can plot your, for a given drain current, if you, or for different drain currents, when you plot it, you will reach a limiting value of DC gain. We call it intrinsic gain. Intrinsic gain, the value of intrinsic gain varies from technology. For lower technology nodes have lower GM or not product. Okay, so as you decrease your channel lengths, it becomes smaller and smaller. It can be higher in higher technology. It can be as high as 40 dB or higher in large length, processes. But as you go to smaller and smaller, even to get a 20 dB gain will be challenging. GM or not 20 dB, which means 10. The product GM or not will be less than 10. Okay, so these are the things to keep in mind. Again, keep in mind, even in a lower technology node, let's say you're designing a 45 nanometer device technology using 45 nanometer CMOS process, you can always choose larger channel lengths for your MOS devices. But the problem with larger channel length is you will lose out on speed. Okay, your speed goes, the devices become slower because you'll have more capacitance now. So that's the only problem. But if bandwidth is not a constraint, you can choose larger device lengths, even in lower technology nodes, which is what we normally do. Okay, when you're designing some current mirrors or some biasing circuits, we often choose larger lengths, device lengths in analog circuits. even in lower technology nodes. But digital circuits, when you're designing digital standard library cells, most of them will operate at the least possible lengths. Now, this is the background that you need to know before you design analog circuits. So there are a few things you have to keep in mind, that as you increase your GM is something that's under the designer's control. If the transistor is in weak inversion, or sorry, strong inversion, I know that my GM is, I can increase my GM for a given current by increasing W values. And you also know that intrinsic gain is inversely proportional to 1 by root I, or proportional to root of W by I. These results are valid under strong inversion conditions. Under weak inversion conditions, your GM is proportional to the drain current, or I, drain current here, and your intrinsic gain is constant. There is a fundamental limiting value, and that actually generally depends upon length. Okay, assuming you have fixed W by L ratio on for a given current and given W by L ratio, larger channel lengths will give you better intrinsic gain because your R naught improves. GM remains the same, but R naught improves. So you end up getting better intrinsic gains. Okay, then usually there will also be some second order effects. Your VT, the MOS VT will also change with channel length. So you will see a combination of effects, but I gave you a rough idea. Okay, so this is something you have to keep in mind. So what engineers do, as I said, most engineers operate on some rule of thumb. So before you start a design, you will have some idea about a given technology. So first you take a MOSFET and study its, you just give quickly, let's say you can diode connect a MOSFET, push a current into it and increase the sizes, vary its sizes. Let's say you push up 1 milliampere current and study the single device. Generally, the rule of thumb that we use is that the ratio GM over I. Okay, this ratio GM over I is a constant, right? GM is proportional to I, so the ratio will be a constant. It's generally equal to 20. Okay, GM over I, the ratio will be 20. In fact, where does the 20 come from? It comes from 1 by 4 VT. So if you see GM is I by 4 VT, so that ratio, I'm sorry, it's 1 by 2 VT. GM over I is 1 by 2 VT. So 1 by 2 VT is 1 by 50 milli. 1 by 50 milli is 20. That's where that ratio comes from. So we say that if you are burning 1 milliampere of current, you cannot get a GM greater than 20 milliampere per volt. If you are burning 1 milliampere of current, you cannot get a GM more than this. So this is something like at the back of your head, you just keep this in mind. And what we do, you have to find this GM over I ratio from simulations. It varies with technology. In fact, it can vary from lower technology nodes. It can be 45 nanometer, it can be very low. It can be as low as 10 or even lower. But usually 10 to 20 is a good number. 180 nanometer is a large technology, like it's 180 nanometer compared to 60 and all that, it's 3 times lower, 60. So by that you can expect 20 milliamp, GM over I ratio of close to 15 to 20. You can expect something in this range. So these are the facts you have to keep in mind before you start designing the circuits. Okay, so strong inversion, how do you know if it's in strong inversion? You can see your V overdrive. If they are greater than 150, if they are in the order of 200 and above, you know that it's in strong inversion. So in that region, these results will be valid. When you are in weak inversion, your overdrive voltages will be less than 100 millivolts. Okay, less than or close to 100 millivolts or lower than that, you will know that it will be in weak inversion. In fact, you can read it from a DC operating point test bench. You can read what region it gives you. That will be weak inversion or subthreshold region of operation. So you have to keep all these points in mind. Okay, GM over I, 20, you cannot exceed that. This is just a rule of thumb. So if an engineer is quickly designing how good your amplifier design is, the first thing we'll do is just look at using these quick calculations. We'll see if you're meeting the specs or not, or if you're just exaggerating your design. You'd get to know by these rule of thumb analysis. Now we'll come back to the common gate and common source amplifiers. Now the design rule here, the design problem here, it is given that we have to meet a gain of 50. That's what is given in this problem. We need to achieve a gain of 50. We just saw that the common gate stage, common source stage, and common drain stage, of the three stages, these two stages give you nearly the same gain. If you ensure they both are carrying same currents, you will more or less get the same gains. Okay, especially in strong inversion region. The third stage is a common drain stage, is driving a resistive load. When you're driving a resistive load for a common drain amplifier, so here resistor is 100 ohms, I can assume that my R0 is going to be in the order of few kilo ohms or even close to tens of kilo ohms. So then I can ignore R0 in calculations. I'm going to get a gain of GMRL by 1 plus GMRL. Right? It's a impedance transformer. This circuit is an impedance transformer. The same output voltage will be transferred here, but with a much lower impedance. Impedance will be 1 by GM. You can, using that, you can show this to be the expression for gain. And this number will always be less than or equal to 1. Now, if I'm given the task of deciding what should be the gain, okay, I know that the last stage cannot give me, the common drain stage cannot give me a gain greater than 1. So I can choose the gain to be 0.9 or even 0.8. I can choose it to be 0.8. The first and second stages is where I should get all the gain from. The gain greater than 50 has to come from first and second, because the third stage is just a common drain. You don't get much gain out of it. And as I said, if I give equal currents, then the gain is split equally. So I can assume, for example, a gain of 7, 7, and 0.9. Because I'm assuming equal gain. 7 is 49, which is close to 50. But you get a number less than 50 if I choose 7 and 7. So I'll choose 8 and 8. So if I choose 8 and 8, then I have 8 and 8 is 64 times 0.9. You will get something like greater than 54, which will be slightly more than 50. So I'm fine with that. So I'm going to split my gain this way. I'm giving equal gains because they both are, if you look at the gain expression, they are more or less giving me the same gain, which is close to intrinsic gain by 2. Okay, so 6 dB lower than the intrinsic gain, so I'm fine with that. So that's going to be 8 and 8 here. Okay, and the third stage will be 0.8. So if your intrinsic gain depends upon the channel length, if you choose larger channel length, then you can get very, very high intrinsic gain. So you can easily get greater than 20, and this is 180 nanometers, so you should be able to get even higher intrinsic gains. Okay, in the order of 40 dB, you should be able to achieve. So these are all achievable numbers. That is the next step. I know I've split it, and then I know that 3 are achievable. Now the next step is, how am I going to assign? See, eventually when you talk about amplifier design, what are the things we have to care about? We have to care about the W by L ratios. What am I going to choose as W by L ratios? Okay, that is one thing. And what are the bias currents that these devices are going to carry? Once you set these two, then everything is set. So to do that, we have to take the voltage swings into consideration. Voltage swing and power dissipation. These two will decide what will be my W by L ratios and current numbers. So if you look at the circuit, as I said, these two stages are driving capacitive loads, right? They are driving capacitive loads, and we just saw that the gain is independent of the bias current in subthreshold region. And even if I bias it in strong inversion, it's proportional to 1 by root I. So I can get very good gains even by burning very low currents in the order of, let's say, less than 100 microamps. I have a spec of 12.5 milliamps. Okay, I don't need that much current in first two stages because they are just gain. They are there only to give me the gain. Okay, so all I need to do is ensure that all transistors are in saturation. And when I say in saturation, even when the output is swinging, all transistors are supposed to be in saturation. Okay, that is something that I have to ensure by design. And I just said that the first two stages don't need, they are there only to give me the voltage gain, and they don't need much power. See here again, noise is not mentioned, bandwidth is not mentioned, none of it is mentioned. So those will usually dictate the current numbers, but here none of it is given, so we don't have to worry about that. So first two stages I can burn as low current as possible and get the gain numbers that I want. Okay, so I'll not worry about the gain in the first two the currents in the first two stages. The third stage is where the maximum current spec goes into. Okay, the third stage, if you look at it, I'm just going to draw the third stage alone here. So which is a common drain. So this is a 2 volts and you have a MOSFET here. So I'll treat this is actually a current source. Okay, I'll come to biasing circuitry later. This is actually a current source. If I draw the circuit, right, so the circuit is going to look something like this using current sources. So I'm driving this with a input voltage source. This is biased using a current source. And then you have a common source amplifier, which is again biased using a current source. The output goes this way. Okay, those three MOSFETs that you see that you saw in the figure, they are there to generate, they are just acting as current sources. Okay, so this again is at some bias voltage, and that bias voltage is just set using some biasing circuitry. So now you have a resistor RL here. We have to talk about how am I going to choose my W-bell ratios and all that. Now it's given that the total swing that you're supposed to design this circuit for is 0.8 volts, which means around some DC voltage, let's call it VODC, that's the output DC voltage. Around that it has to swing 0.8. Let's assume it is symmetrically swinging. So 0.4 volts above and 0.4 volts below VDC. It's going to swing 0.4 below and 0.4 above. The next step we have to decide in this circuit is the overdrive voltages that I'm going to design it for. So when you design a MOSFET for whatever be the bias current that you're going to choose, the VGS of the MOSFET is equal to VT of the NMOS plus the overdrive voltage. Now let's assume that we are biasing them in strong inversion. So I'll assume that overdrive should be at least 200 millivolts. Let's assume for analysis sake, I'll assume them to be 200 millivolts. So that's what I'm going to design it for. I'll choose my W-bell ratios. If I'm meeting anything 200, slightly around 200, I'm fine with it. Okay, I'll set the overdrive voltages to be at 200 millivolts, which means if I fix my overdrive, I'm fixing my gate to source voltage. So the gate to source voltage is VT plus 200. Now again, I'm going to make another assumption for 180 nanometers. The VT, if I remember, it's been long since I designed a 180 nanometer device, used 180 nanometer devices, but it's somewhere around 400 millivolts. I think it's even higher for some devices. There will be a flavor of devices called low VT devices, which will offer you lower threshold voltages. But the VTs can be expected to be even higher in lower technology nodes. But 400 millivolts is a reasonable number. So I'll assume VT to be 400 millivolts. It may be a little off, but I'm going to take it as 400 millivolts. So 400 millivolts plus 200 millivolts is 600 millivolts. So this is what I'm going to design for all my transistors. All my transistors will have 600 millivolts of VGS. Okay, all my transistors will need 600 millivolts of VGS. So if I choose 600 millivolts of my VGS, the minimum voltage necessary to keep my transistors in saturation, the drain to source voltage is 200 millivolts. Right? You need to at least ensure that VDS should be greater than VGS minus VT for it to be in saturation. So minimum voltage on the lower transistor is 200 millivolts. So as the output node is swinging, when the output node goes lower, I have to worry about the lower transistor going out of saturation. Okay, so if I ensure that I'll give some margin of say 100. This is again a number I'm using as an approximation. Let's assume 200 millivolts is ideally sufficient, but let's give a 100 millivolt margin so that you don't want to push this device into linear region at any circumstance. That is 300 millivolts. If I set my lower boundary at 300 millivolts, the upper boundary or the highermost voltage is going to be 1.1 volts. Now the drain voltage is at 2 volts, source voltage is at 1.1. This is giving me a 0.9 volt VDS, which is good enough for me, which is sufficiently, the upper device is in saturation, right? The upper device will go out of saturation only at the peak condition because its drain to source voltage is minimum at that point. Okay, so at that point, you have to ensure that your device is in saturation, so that condition is ensured. So we have found that. Okay. So the output node, I have decided it's going to swing from 0.3 volts to 1.1 volts. Now, if you recall, a common drain amplifier is a level shifter. So if the output voltage is swinging with a common voltage, the DC voltage at the output will be 0.3 plus 0.4. So this will be 0.7 volts. So it will swing 0.4 volts above 0.7, 0.4 volts below 0.7. So it goes to 1.1 and 1.3. The gate terminal here is going to swing. The DC will shift. The swing will remain the same because the gain is close to 1. Okay. Swing will remain more or less the same, but the DC voltage will be shifted by the VGS, which is 600 millivolts. So here it will be 1.3 volts. The DC node voltage here, the DC here, they will be 1.3 volts. And you will go 0.4 volts above 1.3 and 0.4 volts below 1.3. So you will go to 0.4 below 1.3 is 0.9 and here it is 1.7 volts. Now if I assume 1.7 volts, we'll again go back to the circuit here. This current source is realized using a single MOSFET. Then I'm still giving, it needs at least 200 millivolts for it to remain in saturation. The maximum voltage this node can go to is 1.7 volts. Therefore, this is getting at least 300 millivolts throughout its operation. So it will always remain in saturation, comfortably remain in saturation through and through. And the lower device, which is the NMOS device, you have to worry about it on the lower end. That's when it can run out of saturation. On the lower end, it goes to 0.9 volts. Again, it will be, that's much greater than 0.2 volts. So therefore, that is also comfortably in saturation region. Okay, so that's the voltage swing at this node. So we have seen all the transistors are now remaining in saturation. Okay, and finally we are back to the input of this, which is these two, the first stage. So I'll just redraw the first stage here. The first stage. So when I'm doing DC biasing, I can short circuit the input source because it's an AC source, and we just saw that this node output voltage is swinging 0.8 volts around a DC of 1.3 volts. It's going to a maximum of 1.7 and minimum of 0.9 volts. And we said that both the transistors are in saturation. This stage, the gain here, because it's amplified by 8 times, you have to do 1 by 8 of this. So if this node is swinging by 800 millivolts, the node here, the output of the first stage, will swing by 100 millivolts. So the voltage swing is just 100 millivolts. Okay, and what is the DC voltage there? That DC voltage is set by this MOSFET, which will be 600 millivolts. So the DC voltage is 600 millivolts plus minus 100. 600 millivolts. So it will go to 700 milli on the upper side and 500 milli on the lower side. Again, both these conditions, all the devices will be in saturation region. Okay, the upper device still has a huge margin. It's only going till 700 millivolts, so it has almost 1.3 volts across it, even worst case. A lower device has at least 500 millivolts across it in the worst case, when it goes to the lowest possible node voltage. Okay, and the output, the first stage output is at its lowest possible output voltage. So by choosing 200 millivolts of overdrive voltage, assuming a VT of 400 millivolts, so this you have to verify in your design what is the VT. I've just told you the procedure. You may have to alter this number by a few millivolts, tens of millivolts if your VT is higher or so on. Okay, so that decides all the overdrive voltages. VGSs are all set. Now finally we are coming to the currents. What are the currents am I going to set for these devices? Okay, so I'll start with the last stage because that is being driven by you have a current source and a resistor directly. So normally you put a capacitively couple it, but here it looks like it's directly connected. So we just said that the DC node voltage here is 0.7 and the maximum it can go is 1.1, minimum it can go is 0.3 volts. So at DC, so if I plot the current that is going through the resistor, you have two currents. One is IB, this is the bias current, and the current flowing through the resistor, which is a sinusoidal current. So which has a DC component plus an AC component. The DC value is given by 0.7 by RL. So that turns out to be 0.7 by 100, which is 7 milliamperes. So the resistor carries a DC current of 7 milliamperes. Now how do I decide the bias current here? I just said that the DC gain, you can approximate it to 0.9. If I want to get a DC gain of 0.9 from this, then your GMRL by 1 plus GMRL equals to 0.9, then the ratio GMRL, the product GMRL should be equal to 9. So then if I assume RL as 1 by 100, I get a GM of 9 into 10 power minus 2 or 90 milliampere per volt. So this is where that number comes in handy. I told you guys, the maximum GM you can get is 20 milliampere per volt for a 1 milliampere current. So if I burn 1 milliampere, I can expect to get 20 milliampere per volt. So to get 90 milliampere per volt, I need to burn close to 4.5 times or nearly 5 times of 1 milli. So 5 milli of current has to be given to this stage. Okay, that is assuming subthreshold operation, but you will get, depending on the process, you should be able to reach. So 5 milli is a reasonable number. So totally the DC current that this last stage is carrying is approximately IB, I'm assuming to be 5 milliamperes plus 7 milliamperes, which is 12 milliamperes. So that DC current that the last stage is carrying is 12 milliamperes. Now remember, the current cannot exceed 12.5 milliamperes. That is the peak power dissipation. You cannot exceed this number. That's what was given to us. Okay, you cannot exceed this number. Fine. So since you cannot exceed this number, now you are left with 0.5 milliamperes. Now that is still 500 microamperes, which is still a lot of current. I can easily bias the first two stages. Since I said the first two stages, since they are in strong inversion, the lower the drain current, the higher the DC gain I can get out of them. So that you can choose even 100 microamps for the first two stages. And some of the first two stages, you can give 50 microamp each, 50 microampere to each of the devices and still keep them in saturation region. Okay. Now finally coming to the biasing arm design. So I'll just discuss one small circuit before I go to board talking about the biasing arm. So let's say we have, how do we normally decide currents that flow into, ensure that the devices are carrying the right currents? The simplest biasing scheme can look like this. You can have a known current flowing through a diode connected device, then that sets the VGS necessary. This I can use it as a VGS for biasing a current source. Okay, this current source can go as a current source load for common source amplifier, or I've shown an NMOS version. You can also assume a PMOS version where use a diode connected device to set the gate to source voltage, and then here I have a common source amplifier which is biased using a current source. Okay, so I need to set this gate voltage by some means, the right gate voltage. So and what is that right gate voltage? In our example, we said that if your supply is 2 volts giving 600 millivolts to this node voltage should be at 1.4 volts. That's what I should set it to. Okay, to bias it properly, I need to set this to 1.4. And similarly, if I want to bias my common gate amplifier, okay, see, that's just assuming source voltage is 0, DC bias conditions, the structure looks like this. Common gate amplifier, the first stage, M1, M2, looks something like this. So you have VDD, and I need to set these two bias voltages. This bias voltage should be 600 millivolts, and this bias voltage should be 1.4 volts. So how do I set both these bias voltages? One other way of doing, if I don't have current sources, I have only resistors and MOS devices, then all I can do is just do a diode connected biasing. Now the current through this device is given by I equals VDD minus VGS upon R. Now VGS has a square root relationship with the drain current. So you will get a nonlinear equation something like this. So you will get VDD by R minus VGS by R. VGS is again VTN plus root of 2i by 2i by beta n, where beta n is mu and Cox W by L. So you get an equation. This equation has to be solved so numerically to find the right value of resistor and W by L of NMOS, so that you get this to be 600 millivolts. So you have two parameters to vary. You have the W by L of this NMOS and the resistor. You can start with some value, slowly tweak it till you get this VGS to be 600 millivolts. Once you have that, you can directly connect it to this. Okay. Now, but in this circuit, you have to also generate a PMOS bias as well. So what they did was that they did something like this. So they have a resistor and a diode connected device. Okay. So let's call this R1 and R2. So this is VDD. Let's say you set your current by some means. You can choose a certain value of R1 and R2. So remember, since you are burning 12 milliamp, I think it's 12 milliampere in the last stage, and then 100 microamperes in the stage 1 and stage 2, you can assume that, okay, you won't exceed, you can spend another 100 microampere in the biasing arm. You can spend another 100 microamperes here. So once your 100 microampere current is fixed, times R1 should be 600 millivolts. So 100 microampere times R1 should be 600 millivolts. So from that you get the value of R1. So 0.6 by 100 into 10 power 6, 4, so 6 kilo ohms. So you get R1 of 6 kilo ohms. So this will set this node voltage at 1.4 volts. So here I'm assuming I'm by design. How do I choose that current? I can still vary R2 and the W by L ratio of this MOSFET so that the bias current is at 100 microamps and the VGS should be 600 millivolts. Okay, so then once this is done, this can be fed to the PMOS gates. This can be fed to the NMOS gates for DC biasing. So I think I'll go back to the first circuit. This is how it is shown here. So this is 600 millivolts. That sets the DC bias for this guy. Then this node will be at 1.4 volts, which sets the DC bias. So both will be at 600 milli and this will be at 600 millivolts. So now all the biasing is complete. Okay. First you should do a DC analysis and then do an AC analysis. In the AC analysis, or you can even perform a transient analysis. AC analysis is to verify the gain. Are you getting the right gain or not? So we said this is, if this is swinging by 0.8, this will also swing by 0.8 volts. I mean, in fact, it will swing by 0.8 into 1 by 0.9, right? Since if I chose GMR0 to be, GMRL to be 9, the gain of this stage is 0.9. So divided by the gain is the swing at this node. Then this node swing will be 1/8 of that. So 1 by 7.2. Now the swing at this node will be 1/8 of this value. So it will be 1 by 7 into 8, right? So I think 56 will be the value at this point. Okay, 1 by 56. So if this is 100, if this is swinging close to 100 millivolts, 1/8 of that, this will be 12 millivolt, 12.5 millivolt swing. So on top of this node, the VGS will keep decreasing or increasing by 12.5 millivolts. Okay, so you can perform a transient analysis finally to verify if your swings are met properly. And in a AC analysis, you can perform to get the DC gain value and verify if it is matching any value greater than 50. Okay, so 100 dB, if you have a gain of 100, it is 40 dB. 50 will be by 2, so it will be 34 dB. So any value of gain greater than 34 dB, you're fine. Okay, you do an AC analysis and find out the gain. It should be greater than 34 dB. Okay, so mind you, I've given you one approach to design the circuit and some important points to keep in mind when designing. That's how analog engineers think. Okay, before you start a design, you know intuitively how much current do you have to burn to get a certain GM. Okay, and keeping that in mind, we can design. And I just told you just choose 100 micrograms or 50 microgram for each of the stages, and not worry much about how am I going to get the gain. But as I said, if you keep increasing your W by L, your devices will go into subthreshold and the gain will reach a limiting value, which will be, it can be as high as 40 or 50 in large channel devices. And short channel devices, it can be very low. You can have a gain of as low as 10. Okay, GMR0 product will be, intrinsic gain will be as low as 10. So 180 nanometer, you should be able to get decent gain. In case you're not getting the decent gain, increase your channel lengths. Okay, you're increasing your channel length, you will make it R0 will be improved. So you get better DC gain out of those devices. Okay, you will lose out on bandwidth, but in this problem, bandwidth is not a constraint. There is one problem with this circuit. So if I wouldn't design a question like this. There is a problem with biasing single-ended amplifiers. When you give a current with a current source load, and the biasing is usually quite problematic. Okay, so even if when you're analyzing this, you will realize that when you're tweaking some small W/L ratios here and there, you will see some sudden weird changes at the output. I'll explain why that happens in a later video. I usually, my assignments when I designed it for my students when I was teaching, I will not give the problems this way. Okay, it will be slightly different, but probably this is a good question. In one question, they are testing your understanding of all the three amplifiers: common gate, common drain, and common source. Okay, so I gave you an idea how to split the gains. This is where you do typically when you're designing multi-stage amplifiers. You see which node is driving capacitive and resistive loads and give maximum gain to the capacitively loaded nodes. Okay, and this is the way conventionally, if you look at audio amplifiers, they will have a gain stage and a driver stage. The final stage is what we call a driver stage. It's driving a resistive load. Okay, it's generally a power amplifier which is delivering some power. Okay, so you can actually calculate. I didn't calculate the power here. You can calculate the power that you're delivering to the resistor. So the resistor is 100 ohm. You're injecting two kinds of. There is a DC voltage and an AC voltage. So the AC power is V peak to peak square by 8R. Okay, that's you can just quickly derive yourself. It will be, you know how to find RMS power. That will be V peak to peak square by 8RL plus VODC square by RL. This will be the total power dissipated across the resistor. Okay, so VODC here is 0.7 whole square by 100 and V peak to peak square is 0.8 whole square by 800. So you can just plug in and compute those numbers. That will be the power that you're delivering to the load resistor. Okay, that will obviously be greater than the power drawn from the supply. Power drawn from the supply will be VDD into I average. Okay, that's the power drawn. That will be the, because that power, some of it goes into biasing the transistors. That's a wasted power. So this is the final power that is delivered to the resistor. Okay, I think this point comes to 4.9 milliwatts or something. Okay, so 0.49 into 10 power minus 2, and this one comes to 0.64 into 10 power minus 2 by 8, so 0.08, so 8 milliwatts. So 8 plus 4, 8 plus 5 is 13, so 13 or 20, 12.9 milliwatts. That's the power you are delivering to the resistor. If you want to decrease the power delivered to the resistor, all you need to do is decrease the DC voltage. So right now I said the DC voltage is at 0.7, 1 volt, 0.4 and zero point 0.4 below 1.7, that's the DC swing, okay, or the voltage swing. I can also slightly reduce this. I can by 100 millivolts, because to keep the current source in saturation, I just need 200 millivolts. I don't need 300. So I can slightly decrease this. 0.7 can be made 0.65, and I can save some power. It's a very decent saving of power. If I go to 0.7 to 0.6, I will be saving the DC power by nearly a milliamp, more than a milliamp. Okay, so that will be a decent saving. So these are some points to keep in mind. Okay, so that's it. I think I've discussed more or less everything that needs to be discussed about this problem. In case if you have any questions, you can just post as a YouTube comment or send me a message. Whenever I find time, I'll reply back. Thank you.